A 3-ton shipping container folds around a concrete bridge piling like a strip of warm chewing gum. The steel chassis of a parked sedan shears in half, not from an explosion, but from the sheer lateral pressure of brown sludge moving at 12 meters per second. This is not the sound of flowing water. It is a deafening, mechanical grinding. A continuous, low-frequency roar generated by granite boulders the size of compact cars smashing into one another beneath the surface. The asphalt beneath your feet vibrates with the intensity of a passing freight train. A storefront window, designed to withstand hurricane winds, shatters instantly as the pressure differential spikes. The street is no longer a street. It is a pressurized injection nozzle for 1 billion liters of debris-laden fluid. There is no rising tide. There is no warning siren. There is only a vertical wall of kinetic energy arriving with the speed of a highway chase. 1 second, the pavement is dry. The next, the atmosphere is replaced by a slurry that weighs twice as much as pure water, and moves with enough force to tear reinforced concrete from its rebar skeleton. The destruction is absolute, and the timeline is measured in heartbeats. Let's find out. Most turn away. But here at Surphysia, we decode the math behind the chaos. Support the mission by subscribing now. To understand why a flash flood kills with the efficiency of a predator while a river flood behaves like a siege engine, we must first strip away our psychological comfort with water. We view water as soft, yielding, and life-giving. This is a fatal biological error. In the world of physics, water is a non-compressible fluid with a density of 1,000 kilograms per cubic meter. That means a single cube of water, 1 meter on each side, weighs exactly 1 metric ton. It is the same mass as a small electric vehicle. When you stand in a gentle stream, you are essentially standing next to a parked car. But when that water begins to move, the equation changes from simple hydrostatics to terrifying hydrodynamics. The comparison between a river flood and a flash flood is not merely a difference in location. It is a fundamental difference in how energy is stored, transported, and released. It is the difference between a glacier and a bullet. Both are ice, both are dangerous. But only one kills you before your brain processes the visual input. Let's first dissect the slow-motion catastrophe, the river flood. This is the mechanism of the siege. It begins thousands of kilometers away, often weeks before the water reaches your doorstep. A low-pressure system stalls over a vast catchment area. Perhaps 50,000 square kilometers of basin. The rain falls steadily. The ground, initially thirsty, acts as a sponge. The soil matrix absorbs the moisture, filling the microscopic voids between silicate particles. But eventually, the soil reaches saturation. The sponge is full. The friction that holds water in place is overcome by gravity, and the runoff begins. This is a cumulative disaster. The tributaries feed the streams. The streams feed the secondary rivers, and they all converge into the main channel. The water level rises, centimeter by centimeter. In a river flood, the primary physical force at play is hydrostatic pressure. This is the pressure exerted by a fluid at rest or moving slowly. As the river widens and deepens, the weight of the water column increases. If a levee holds back 6 meters of floodwater, the pressure at the base of that wall is immense. Nearly 60,000 Pascals. This is the equivalent of a large African elephant balancing on a small dining table, pressing against every square meter of the wall's base. However, the velocity is often low. The water spreads out across the floodplain, dissipating its energy over a wide area. The danger here is volume and duration. The water surrounds structures, soaking into the masonry, dissolving the gypsum and drywall, and rotting the wooden framing. It exerts a buoyant force on foundations. If a house is not anchored, the Archimedes principle takes over. If the displaced weight of the water is greater than the weight of the house, the structure lifts. It becomes a boat. But because the velocity is low, the house might float gently away or simply settle into the mud. The river flood allows you time. You can see the gauge rising. You can pack your bags. You can drive to higher ground. The energy is vast, but it is distributed over days and weeks. It is a crushing hug, slow and inevitable. Now, we accelerate the timeline. We strip away the vast floodplain and introduce the topography of a trap. This is the flash flood. The physics shift entirely from potential energy to kinetic energy. The mechanism of the flash flood is the sudden, violent conversion of altitude into velocity. It often begins in a localized area. A slot canyon, a steep mountain valley, or an urban concrete jungle. A thunderstorm dumps 10 centimeters of rain in 1 hour onto a surface that cannot absorb it. This could be non-porous desert sandstone or the asphalt grid of a city center. There is no soil saturation phase. There is no sponge. The runoff coefficient hits nearly 100% instantly. Gravity grabs this water and pulls it down the gradient. In a river, the water has room to spread, which increases friction and slows it down. In a flash flood scenario, the terrain often funnels the water. This is the Venturi effect on a geological scale. As the canyon narrows, the fluid must speed up to maintain the flow rate. The velocity spikes. We are no longer talking about a lazy 2 meters per second. We are seeing velocities exceeding 10, 15, sometimes 20 meters per second. Here is where the math turns lethal. The force exerted by moving water does not increase linearly with speed. It increases with the square of the speed. This is the drag equation. If you double the speed of the water, the force it hits you with quadruples. If you triple the speed, the force increases by a factor of 9. A flash flood moving at 10 meters per second hits with 100 times the force of a river moving at 1 meter per second. This is why a mere 15 centimeters of fast-moving water, ankle deep, can knock a grown human off their feet. The human body is not a hydrodynamic shape. We are bluff bodies. We create turbulence. The water piles up on the upstream side of your legs, creating a high-pressure zone, while the downstream side creates a low-pressure wake. This pressure differential pushes you down current with shocking aggression. But a flash flood is rarely just water. This is the critical variable that most people fail to calculate. As the water tears down the canyon or the street, it scours the surface. It picks up sand, clay, rocks, trees, and cars. This transforms the fluid from water into a debris flow. The density of the fluid skyrockets. Remember, clear water weighs 1,000 kilograms per cubic meter. A thick, turbulent debris flow, a slurry of mud and rock, can reach densities of 2,000 to 2,500 kilograms per cubic meter. It is essentially liquid concrete. Let's freeze time at the moment of impact to understand this density multiplier. A wall of this slurry hits the side of a building. The calculation for the impact force involves both the density and the velocity squared. You have increased the velocity by a factor of 10, multiplying force by 100. And now you have doubled the density, doubling the force again. The result is an impact force 200 times greater than a standard river current. When this slurry strikes a wooden frame house, it doesn't flow around it. It functions as a battering ram. The kinetic energy transfer is instantaneous. The studs snap. The load-bearing walls shear. The house is not flooded, it is erased. Consider the leading edge of a flash flood. In a dry wash or a narrow street, the friction against the dry ground slows the very front of the water, causing the faster water behind it to pile up on top. This creates a literal vertical wall of water, rocks, and timber. A bore. This bore can act like a solid object. When witnesses describe a roar like a jet engine, they are hearing the acoustic energy of thousands of tons of rock grinding against the bedrock, transmitted through the ground and the air. The vibration alone can be felt kilometers away. This mechanical grinding pulverizes everything in the flow path, adding more fine sediment to the mix, which further increases the viscosity and density, creating a self-reinforcing cycle of destruction. The kill factor of the flash flood is the elimination of reaction time. In a river flood, the sensory inputs are gradual. You see the water rising. You smell the damp earth. In a flash flood, the environment remains normal until the final seconds. You might be hiking in a slot canyon under blue skies, unaware that a storm cell has burst 20 kilometers upstream. The canyon walls, polished by millennia of erosion, are perfect conduits for sound and water. The first warning is often a change in wind direction. A sudden cool breeze pushing down the canyon, displaced by the rushing mass of water. Then comes the smell of ozone and pulverized earth. Then the sound. By the time you see the wall of brown sludge rounding the bend, the math has already sealed your fate. You cannot outrun a flow moving at 15 meters per second on uneven terrain. You cannot climb a vertical sandstone wall in 3 seconds. Let's analyze the interaction between a flash flood and a modern vehicle. The metal cage we often mistakenly believe offers safety. A standard sedan weighs perhaps 1,500 kilograms. It sits on 4 rubber patches, the tires, which offer friction against the road. Friction is the only thing holding the car in place. But water reduces that coefficient of friction to near zero. Furthermore, the chassis of a car is designed to be aerodynamic, not hydrodynamic. It is essentially a hollow steel bubble. As the water rises past the chassis, buoyancy kicks in. The car displaces water. If the water is rising fast, the car loses contact with the asphalt before the water even reaches the windows. It floats. Once the car is floating, it is at the mercy of the current. But in a flash flood, the current is turbulent and chaotic. The water isn't just pushing the car, it is rotating it. The moment the car turns broadside to the current, the surface area exposed to the flow increases dramatically. The drag force spikes. The car flips. Now, the occupants are upside down, in a dark, pressurized, tumbling steel box, submerged in a slurry of liquid concrete. The windows are pressed inward by the weight of the mud. Opening a door against the pressure of rushing water is a physical impossibility. A mere half-meter of differential water height on a car door exerts hundreds of kilograms of force against it. You cannot push it open. The flash flood converts the vehicle from a sanctuary into a tomb in less than 5 seconds. The urban environment exacerbates the violence. We pave our cities with asphalt and concrete, creating impermeable surfaces that reject water. We channel streams into concrete culverts and storm drains designed for average, historical storms. When a storm exceeds these design parameters, the infrastructure backfires. The streets become artificial canyons. The smooth pavement offers almost zero friction to the water, allowing velocities to remain high even on shallow gradients. A flash flood in a city is a channeling of the entire sky's output into a grid of narrow chutes. Basements become pressurized traps. The subway systems become siphons. The speed at which a subway tunnel fills is dictated by the diameter of the entrance and the height of the water above it. A straightforward hydraulic calculation, but one that results in millions of liters of water plunging underground in minutes. In contrast, the river flood is a test of endurance. It tests the engineering of dams, the height of levees, and the zoning laws of a region. It is a static load test. Can this earthen berm withstand the hydrostatic pressure for 3 weeks? Can the pumps outpace the seepage? It is a battle of attrition. The flash flood is a shock test. It is an impact event. It tests the sheer tensile strength of materials and the reflex speed of biological organisms. The river flood allows for the rescue of property and the evacuation of populations. The flash flood demands that you abandon everything instantly. The psychological delay. The normalcy bias, where the human brain refuses to accept that a sunny street is about to become a death zone, is the most lethal factor. By the time the brain accepts the reality of the wall of water, the window for action has closed. We must also consider the aftermath, which reveals the difference in energy deposition. A receding river flood leaves behind a layer of fine silt, a waterlogged landscape, and mold. It leaves the structure standing, albeit damaged. A receding flash flood leaves behind a new topography. It deposits boulder fields where parks used to be. It erases roads entirely, scouring down to the bedrock. It leaves cars wrapped around trees 5 meters in the air. The energy required to lift a 2-ton vehicle 5 meters vertically is immense. And the flash flood expends this energy casually. The atmosphere itself is the engine, but the terrain is the weapon. In a river flood, the terrain is a passive bowl. In a flash flood, the terrain is the barrel of a gun. The steep slopes of a mountain burn area, stripped of vegetation by a previous year's fire, become frictionless slides. Ash and soil, hydrophobic due to the intense heat of the fire, repel the water, increasing the runoff speed. This fire flood sequence is one of the most destructive geologic phenomena known. Creating debris flows with the consistency of wet cement that can travel dozens of kilometers from the rain source, striking communities that never saw a drop of rain. The comparison is clear. The river flood is the inevitable crushing weight of the atmosphere's moisture budget, distributed over time and space. The flash flood is a concentrated injection of kinetic violence, a localized failure of the Earth's ability to manage energy. It utilizes the density of mud, the velocity of the drop, and the geometry of the canyon to create a force that biological evolution has not prepared us to withstand. We are built to run from predators, not from a liquid wall moving at highway speeds. Ultimately, the physics are indifferent. The water molecule does not care if it is part of a rising tide or a crashing wave. It simply obeys the laws of gravity and fluid dynamics. But for us, the distinction is everything. One allows us to pack our memories in boxes and drive away. The other demands we leave the boxes, leave the car, and climb. The margin for error in a river flood is kilometers and days. The margin for error in a flash flood is meters and seconds. The universe is full of chaos, but we are here to decode it. Stay connected to Surphysia.